Hi, I am Juan Pablo Zamora Zapata, Business Development Director of NordiaSoft, a company that specializes in software-defined systems. Today, through a series of demonstrations, we are going to highlight some features of the software communications architecture, the SCA, features that enhance software application portability across different target systems. For our demonstration today, we are going to run an analog FM waveform application in 4 different target systems. The first one is a test instrument. Actually, it's a software-defined test instrument that today we're going to use just as a software-defined radio. Second demonstration will use a laptop computer to execute the same FM waveform application. Third demonstration will run on a Samsung smartphone, and I'll leave the 4th demonstration details for the future. To achieve those demonstrations, the first one is a self-contained system that possesses both processing and RF capabilities. Moving forward to the laptop, well, the laptop doesn't have capability of transmitting and receiving, so instead we're going to use an external RF transceiver, an Ethos Research USRP box that will allow me to communicate over the air with an FM handheld radio. Part of the demonstration, we will also use a Wi-Fi router, some speakers, and a small video projector. So let us start with the first demonstration, in which we're going to be using this test instrument. We said it was a software-defined test instrument that today we will be using as a software-defined radio. This is a self-contained unit that has everything I need for the demonstration. It has processing capabilities as well as an RF transceiver that will allow me for communication over the air with my handheld FM radio. But before we start with the actual demonstration, let me introduce a key feature of the SCA that enhances application portability. That feature relies on hardware abstraction for an SCA waveform to be able to be moved from one platform to the next. An SCA application is not permitted to use native drivers to interact with the physical hardware. And the reason, well, should be obvious. It's because the moment that we use native drivers to interact with an application, that application becomes tied with the physical hardware, with the physical platform. And when we want to move that application to the next platform, then we have to remove everything that was specific to the previous hardware so we can start making the port towards the next platform. So what the SCA does, again, it abstracts the hardware away. What we have on the screen is a graphical representation of all those pieces of hardware that have been abstracted from the physical test instrument. On the far left, I have a representation of 2 pieces of hardware that are part of the transceiver board. At the top, I have an SCA transceiver device that will allow me to transmit and receive over the air. And the second light blue box is a small arm that allows me to do some processing, some execution of software within the same board. In the middle, we have a second board. This one has an i7, an x86 running Linux that will allow me, that will be able to host my waveform application and execute it. At the far right, finally, we have an audio device that will give me access to the microphone and to the speakers of that system, so we can input the voice and reproduce it once transformed. So what I'm going to do now is I'm going to close those three windows that represent our physical hardware, and I'm going to launch the application, the FM waveform application. At this point, the SCA core framework is finding suitable targets for deployment, and now I have my application now instantiated. On the screen, what we have is the entire application. On the far right, we have the audio device, and this is at the bottom we have the transmit path. It means that I'm obtaining samples from the microphone of the audio device, then I'm doing some filtering, resampling, FM modulation, and after a format conversion from short to double, I'm delivering the processed samples towards the RF transmitter for over-the-air transmission. On the receive side, we have the antenna picking up the data samples, then delivering them for data conversion, double to short, and then going through demodulation, resampling, and the processed data is finally delivered to the audio device towards the speakers. So now my application is running, and the second that I start the application, I will immediately hear noise coming out of the speakers, but then I will talk to the radio and I will hear my voice coming through the speakers. So I do right click, start. 1, 2, 1, 2. So that was the receive path. If I were to change that now to transmit, 1, 2, 1, 2, 3. So that was the transmit portion. We have both ways, and this concludes the first demonstration where we used this test instrument as a software-defined radio. We are on to our second demonstration. This second demonstration will run the exact same, very same analog FM waveform, but instead of running it in this test instrument, now we are executing and doing the signal processing in the laptop. A couple of things that I would like to highlight. First, some might quickly ask, well, if we have i7, an x86 processor here, and also an x86 processor here, what is the complexity, or what is what we are talking about portability? Well, yeah, you might be right. In reality, the application is just doing a cross-compile using a different linker, but very similar, and we are now executing on the laptop. But the key difference in this second demonstration is that now we are not using the RF transceiver from the test instrument anymore. Now we're using this external USRP device. And traditionally, this type of development would have made the signal processing of the FM waveform application to rely on one specific piece of hardware. In this case, our entire application is somehow independent of the device that is physically providing the samples for further processing. So the difference in this entire application is just the reference to the device, to the SCA device that will provide us the capability of transmitting and receiving. In the first application, my components were connected to the transceiver device of the test instrument. In this second instance, we are connected, as I said, to this USRP external transceiver. So let us execute the application. We are in receive mode, and you will see below in the screen how there is plotting that will start as soon as I start talking into the handheld. 1, 2, 3, 1, 2, 3. So that was a very quick example of transmitting from the handheld to the USRP signal processed in the laptop. We are going to change now from receive to transmit. And we are going to talk in the microphone, and we will hear it on the handheld device. We are now into our third demonstration, and for this one we are going to use a Samsung smartphone that we will be using it as an FM transceiver and receiver. If you look closely, the only thing that we have on this phone is a simulation of a keypad of a handheld, and that is a plain Jane Java user interface, and the entire FM waveform, the exact same waveform that we've been first executing on the test instrument, then on the laptop. Now we will be running on the phone. The actual demonstration is kind of simple. I will talk on the handheld and I will hear my voice on the phone. 1, 2, 3. 1, 2, 3. I will use the volume button to toggle between transmit and receive. So now I am in transmit mode, and I'm talking into the phone and hearing myself on the handheld receiver. We've reached now time for the last and fourth demonstration, and for this one we will be using this small video projector as a software-defined receiver. If you're asking yourself why on earth would we use a projector as an FM receiver, there might not be a good answer other than show and tell. But the reality is that this is an embedded system that it's basically a software-defined system. It has a processor, it has display capabilities, it has a sound card that will give me access to the speakers. It even has Wi-Fi, so I can communicate with the USRP. So it has pretty much the same elements that I've seen, that I've used in the previous 3 platforms. So what we're about to do now is make this video projector to become an SCA receiver. So first we're going to stop the video capabilities, then we're going to access the native user interface, and we are going to launch the SCA core framework. This SCA core framework is the heart of an SCA system. It's the one that identifies the requirements of all the different components of an SCA application, then looks at the target system, identifies suitable targets, and eventually performs the deployment and execution of the waveform. So now that I've launched my core framework, all I need to do is launch my application. And that application is going to look very similar to the one we used in the Android phone. It's very similar, the same Java GUI. And once it is ready, I will be able to talk on the handheld device and listen to my voice on the speakers of that now SCA software-defined receiver. 1, 2, 3. 1, 2, 3. 1, 2, 3. So we were able to move the same application into 4 different target systems, and we played with a variety of processors. We had x86, we have different models and versions of ARM processors. We had different operating systems, Linux for the first 2, Android for the second 2. We had different sound cards throughout. We had different RF transceivers. And the only thing that remained constant throughout the 4 demonstrations was the exact same FM analog application, an SCA FM application that we were able to easily move from one platform to the next. And with this, we conclude this demonstration. We thank you for listening to us. And if there are any comments or questions, please send us an email at info@nordiasoft.com. Thank you.